Okay, we're trying to discuss question number 9 here. If you haven't read the question, pause the video and read it. The A part talks about evaporation, and we have discussed enough questions in evaporation. All the points in the answers we have discussed earlier in different questions. Still, if you have any doubt, you can post it in the Teams. I will then respond. We will now go to part B, which is in vaporization in latent heat. State what happens to the temperature of the water in the beaker now while boiling is happening, or when there is a change of state happening, then there is no change in temperature. Okay. A change of state is like you can imagine it like this: a person is awake and that person falls asleep, and a person who is fast asleep become awake. Now, when you wake up in the morning, when you open your eyes, yes, there is a tremendous difference that is happening, a great change of state. But your body temperature doesn't change. Similarly, when you are going to sleep in the night, your consciousness is dropped into some place, and there's a great change of state, but temperature doesn't change. But when you start, because as far as your kinetic condition is concerned, it's like the same. But if you start running, the faster you run, the greater the body temperature would be, right? You will become more and more, there would be a raise in your temperature. The same idea, you can just remember this analogy. So change of state is like waking and falling asleep, while an increase in temperature demands an increase in kinetic energy. So what happens to temperature of the water in the beaker? It doesn't change. The specific latent heat of vaporization of water is 2.3 times 10 to the power 6 joules per kilogram. After that, okay, so basically the thing is, there's not any fundamental difference. There might be one or two differences here and there, but the basic ideas would be same. Earlier we had heat capacities. Now we are going to deal with specific heat capacity, latent heat. But the fundamental ideas is like the way of calculating energy and everything would remain the same. So let's extract the information. So the latent heat is given as 2.3 times 10 to the power 6 joules per kilogram. So this is the amount of energy required by 1 kilogram of water for it to become vapor. So this is latent heat of vaporization, LV. And it took the entire volume of water, entire mass of water, which is 0.095 kilogram. It took 12 minutes, and they are asking you to calculate the rate at which energy is supplied. Rate at which energy is supplied, that means energy divided by time. When you hear the word rate, it's always with respect to time, except in common everyday experience where rate means money. In physics, there's no money. In fact, time is the money in physics. So energy divided by time. What is energy divided by time? power, right? So basically the question is asking you to calculate the power at which heat was supplied. So the thing is, time is no issue. We have 12 minutes. Yes, of course there is an issue that we need to convert it to seconds. That's no issue. 12 into 60 seconds. Then we need to calculate the energy. How are we going to calculate the energy? For each kilogram of mass, we need this much energy to convert it to vapor. We have 0.095 kilogram of water. So how much energy we would need? M into LV, right? So 0.095 times 2.3 times 10 to the power 6. Be careful about whether everything is in kilogram or the same unit. Divided by this into this. That gives you the power is equal to 300 watts. It's joules and this is seconds, so joules per second is watts. So if you look at the mark scheme, yeah. So remains constant and 300 watts.